At the end of this video, you should be able to define mole, Avogadros number, and molar mass, and state how all three are related, and solve problems involving mass in grams, amount in moles, and number of atoms of an element. Chapter 3, Section 3, Relative Atomic Masses. Masses of atoms expressed in grams are very small. As we shall see, an atom of oxygen-16, for example, has a mass of 2.657 times 10 to the negative 23rd grams. For most chemical calculations, it is more convenient to use relative atomic masses. As you read in Chapter 2, scientists use standards of measurements that are constant and are the same everywhere. In order to set up a relative scale of atomic mass, one atom has to be arbitrarily chosen as the standard and assigned a relative mass value. The masses of all other atoms are expressed in relation to this defined standard. The standard used by scientists to govern units of atomic mass is the carbon-12 nuclide. It has been arbitrarily assigned a mass of exactly 12 atomic mass units, or 12 AMU. One atomic mass unit, or 1 AMU, is exactly 1/12 the mass of a carbon-12 atom. The atomic mass of any nuclide is determined by comparing it with the mass of the carbon-12 atom. The hydrogen-1 atom has an atomic mass of about 1/12 that of the carbon-12 atom, or about 1 AMU. The precise value of the atomic mass of a hydrogen-1 atom is 1.007825 AMU. An oxygen-16 atom has about 16/12, or 4/3, the mass of a carbon-12 atom. Careful measurements show the atomic mass of oxygen-16 to be 15.994915 AMU. The mass of a magnesium-24 atom is found to be slightly less than twice of that of the carbon-12 atom. Its atomic mass is 23.985042 AMU. Some additional examples of atomic masses of naturally occurring isotopes of several elements are given in Table 3-4 on page 80 of your text or on the screen now. Isotopes of an element may occur naturally, or they may be made in the laboratory, called artificial isotopes. Although isotopes have different masses, they do not differ significantly in their chemical behavior. The masses of subatomic particles can also be expressed on the atomic mass scale. See Table 3-1 on page 74 of your text or on the screen now. The mass of the electron is 0.005486 AMU. That of the proton is 1.007276 AMU. And that of the neutron is 1.008665 AMU. Note that the proton and neutron masses are close but not equal to 1 AMU. You have learned that the mass number of the total number of is the total number of protons and neutrons in the nucleus of an atom. You can now see that the mass number and relative atomic mass of a given nuclide are quite close to each other. They are not identical because the proton and neutron masses deviate slightly from 1 AMU, and the atomic masses include electrons. Also, as you will read in Chapter 22, a small amount of mass is changed to energy in the creation of nucleus from protons and neutrons. Average atomic masses of elements. Most elements occur naturally as mixtures of isotopes, as indicated in Table 3-4 on page 80 of your text or 2 slides previous. The percentage of each isotope in the naturally occurring element on Earth is nearly always the same, no matter where the element is found. The percentage at which an element's isotopes occur in nature is taken into account when calculating the element's average atomic mass. Average atomic mass is the weighted average of the atomic masses of the naturally occurring isotopes of an element. A simple example of how to calculate a weighted average using marbles can be found on page 79 of your text. Calculating average atomic mass. The average atomic mass of an element depends on both the mass and the relative abundance of each of the element's isotopes. For example, naturally occurring copper consists of 69.17% copper 63, which has an atomic mass of 62.9295999 AMU, and 30.83% copper 65, which has an atomic mass of 64.9277793 AMU. The average atomic mass of copper can be calculated by multiplying the atomic mass of each isotope by its relative abundance, expressed in decimal form, and then adding the results. The calculated average atomic mass of naturally occurring copper is 63.55 AMU. The average atomic mass is indicated for the elements listed on table 3-4 on page 80 of your text or on the screen now. As illustrated in the table, most atomic masses are known to 4 or more significant figures. In your book, an element's atomic mass is usually rounded to 2 decimal places before it can be used in a calculation.
Elements can have more than one stable isotope. Helium has 2 stable isotopes, helium-3 and helium-4. Naturally abundant elements have a variety of stable isotopes. Copper is made up of the stable isotopes copper-63 and copper-65. To find the average atomic mass of an element, multiply the mole fraction times the atomic mass for each naturally occurring stable isotope of that element. For example, naturally occurring copper is 69% copper-63 and 31% copper-65. Multiplying these fractions times their respective atomic masses yields the average atomic mass of copper at 63.6 grams per mole.
Relating mass to numbers of atoms. The relative atomic mass scale makes it possible to know how many atoms of an element are present in a sample of an element with a measurable mass. 3 very important concepts, the mole, Avogadros number, and molar mass, provide the basis for relating masses in grams to number of atoms. The mole. The mole is the SI unit for amount of a substance. A mole, abbreviated MOL, is the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. The mole is a counting unit, just like a dozen is. We don't usually order 12 or 24 ears of corn. We order 1 dozen or 2 dozen. Similarly, a chemist may want 1 mole of carbon, or 2 moles of iron, or 2.567 moles of calcium. In the sections that follow, you will see how the mole relates to masses of atoms and compounds.
A mole is a quantity, similar to a dozen. There are 12 items in a dozen, and 6.022 times 10 to the 23rd items in a mole. A dozen eggs, a dozen bagels, and a dozen pencils have different weights or masses and have different properties. The term dozen tells you that there are 12 of the item. Similarly, a mole of iron and a mole of copper have different masses and have different properties, but both represent the same number of atoms, 6.022 times 10 to the 23rd atoms.
Avogadros number. The number of particles in a mole has been experimentally determined in a number of ways. The best modern value is 6.0221367 times 10 to the 23rd. This means that exactly 12 grams of carbon-12 contains 6.0221367 times 10 to the 23rd carbon-12 atoms. The number of particles in a mole is known as Avogadros number, named for the 19th century Italian scientist Amedeo Avogadro, whose ideas were crucial in explaining the relationship between mass and numbers of atoms. Avogadros number, which is 6.0221367 times 10 to the 23rd, is the number of particles in exactly 1 mole of a pure substance. For most purposes, Avogadros number is rounded to 6.022 times 10 to the 23rd. To get a sense of how large Avogadros number is, consider the following. In every living person on Earth, which is about 7 billion people, worked to count the atoms in 1 mole of an element, and if each person, 7 billion, counted continuously at a rate of 1 atom per second, it would take about 4 million years for all the atoms to be counted.
Avogadros number is 6 times 10 to the 23rd. Any collection of this many objects of any kind is called a mole. In general, we use Avogadros number to convert numbers of atoms into measurable amounts of chemicals. Avogadros number is really big. If we covered the lower 48 states with a mole of popcorn, or 6 times 10 to the 23rd pieces of popcorn, the pile of popcorn would be 500 kilometers deep. The layer of popcorn would be twice as high as the International Space Station. But an equal number of atoms of magnesium can fit on this scale and weigh only 24.3 grams.
Molar mass. An alternative definition of mole is the amount of a substance that contains Avogadro's number of particles. Can you figure out the approximate mass of 1 mole of helium atoms? You know that 1 mole of carbon-12 atoms has a mass of exactly 12 grams, and that a carbon-12 atom has an atomic mass of 12 AMU. The atomic mass of a helium atom is 4.00 AMU, which is about 1/3 the mass of a carbon-12 atom. It follows that a mole of helium atoms will have about 1/3 the mass of a mole of carbon-12 atoms. Thus, 1 mole of helium has a mass of about 4.00 grams. The mass of 1 mole of a pure substance is called the molar mass of that substance. Molar mass is usually written in the units grams per mole. The molar mass of an element is numerically equal to the atomic mass of that element in atomic mass units, which can be found on the periodic table. For example, the molar mass of lithium, Li, is 6.94 grams per mole, while the molar mass of mercury, Hg, is 200.59 grams per mole, rounding each value to 2 decimal places. The molar mass of an element contains 1 mole of atoms. For example, 4.00 grams of helium, 6.94 grams of lithium, and 200.59 grams of mercury all contain 1 mole of atoms.
Molar mass. A mole of any other kind of atom or molecule will always contain the same number of particles, 6.02 times 10 to the 23rd particles. The mass, however, will differ because the particles have different masses. Molar mass is the mass in grams of 1 mole of a substance.
Elements can have more than one stable isotope. Helium has 2 stable isotopes, helium-3 and helium-4. Naturally abundant elements have a variety of stable isotopes. Copper is made up of the stable isotopes copper-63 and copper-65. To find the average atomic mass of an element, multiply the mole fraction times the atomic mass for each naturally occurring stable isotope of that element. For example, naturally occurring copper is 69% copper-63 and 31% copper-65. Multiplying these fractions times their respective atomic masses yields the average atomic mass of copper at 63.6 grams per mole.
Gram to mole conversions. Chemists use molar mass as a conversion factor in chemical calculations. For example, the molar mass of helium is 4.00 grams of helium per mole of helium. To find how many grams of helium there are in 2 moles of helium, multiply by the molar mass. Conversions with Avogadros number. Figure 3-11 on page 82 of your text, or on the screen now, shows that Avogadros number can be used to find the number of atoms of an element from the amount in moles, or to find the amount of an element in moles from the number of atoms. While these types of problems are less common in chemistry than converting between moles and mass in grams, they are useful in demonstrating the meaning of Avogadros number. Note that in these calculations, Avogadros number is expressed in units of atoms per mole. At this point, you should be able to define mole, Avogadros number, and molar mass, and state how all three are related, and Solve problems involving mass in grams, amount in moles, and number of atoms of an element.